Good morning to everyone. My name is Daniele. I'm a postdoc at the University of Trento in Italy. And today I'm going to give you a brief introduction to species distribution models. Species distribution models are often applied into the field of biogeography, which is the field of biology and ecology in which we try to understand where and when a species can occur, but also which species and why that species occur in that particular environment. And modeling the distribution of a species might have many reasons. We might want to map the distribution, understand the distribution of a species for conservation practices, such as mapping the distribution of the silverback gorilla in Africa. Or we want to understand the distribution of species with a high economic value, such as livestock or crops as well. Or we want to try to infer and draw some scenarios of climate change to understand how the distributional range of a given species might change under different concentration pathways. Or for public health, we might want to understand how a given species is distributed or might be distributed to inform then epidemiological model about the possibility and the chance of having an outbreak. As in this case, on the left, we have a map showing the habitat suitability for Aedes aegypti, the yellow fever mosquitoes, and this information is used to inform a model for mapping the habitat suitability for dengue on the right side of the slide. In general, what we want to do with the species distribution models is to understand the ecology and the biology of a given species, and then to understand where they can occur in a given place in a given time. Thus, to sum up, we have different purposes that can be inference and explanation of the ecology, mapping and interpolation to understand the spatial distribution of a species, and forecast and transfer to understand how the distribution of the species might change under different conditions. We talked already a lot about the models, ecological models, species distribution models, risk modeling, as the case of dengue. But what is modeling exactly? And basically, you have to try to think modeling as something that naturally occur and something that you commonly do in your head every time you are looking for something. To better understand how an ecological model works, we can try to use a simple example. Think about that you wake up one day and you really want to prepare and have an omelette for lunch, but you don't have mushrooms with you. So what you can do is to go and sample your favorite mushroom species in the forest. And what you try to do when you are looking when you're looking for your mushrooms is to associate the mushroom's presence with the ecological conditions where you can most likely find your mushroom. And if you're lucky, and if you're good enough, in the end you might have a bucket full of mushrooms. But in essence, what you have built in your mind is a relationship between the species, so the mushrooms, and the environment. This is essentially an ecological model. So essentially, species occurs into two different spaces, into the geographic one and into the environmental one. Into the geographic space, the presence of a species is defined by its geographical coordinates, so X and Y. And in this example, we have a species that is mostly distributed into the Mediterranean and Middle East area, but into the coastal area of South America and Central America as well. But into the environmental space, this species occurs mostly between 20 and 30 degrees Celsius of temperature, and between 0 and 1,100 to 2,000 millimeters of precipitation. So it has a very well-defined range of environmental conditions in which it can occur. And indeed, again, what we try to do with a model is to build the relationship between the species and the environment, so the environmental condition in which it can occur, and we define this as this relationship between the species and the environment as the niche concept. And the niche concept is something that has been introduced for the first time at the beginning of the 20th century by Grinnell, an American scientist. And later it was developed several times by other scientists until nowadays, where it is still a debated topic. But today we will focus on mostly on four niche concepts. So the niche concepts of Grinnell, Eldon, Hutchinson, and Soberon and Peterson. In essence, Grinnell defined the niche concept as those environmental conditions that, such as temperature and precipitation, or humidity and so on, that allow the species to survive and reproduce. So there was no biotic component at the time in his view of the Grinnellian niche. Later, Elton introduced a different perspective on the niche concept, based essentially on the biotic conditions, thus on the interaction between species, such as the depredation, parasitins, prey predators interactions, and so on. So these two point of view on the niche were different but complementary. One was based only on the abiotic side, and the other one was mostly based on the biotic side. And in the 50s, for the first time, Hutchinson provided the first synthesis, putting together the fundamental and the biotic niche, and identifying in the overlap between the two the realized niche of the species, which are those environmental conditions where the biotic interactions allow the species to exist and spread. But this we are still missing a piece of the jigsaw in this representation of the niche. And at the beginning of the 21st centuries, Pulliam provided a first definition of the source and sink populations, so defining that species might occur in areas that are unfavorable in terms of climatic or biotic conditions, but they can live there because they have a continuous influx of propagules, so of individuals in those areas. Thus, based also on his studies, Soberon and Peterson proposed a new framework called the biotic abiotic movement framework, the BAM framework, identifying the areas where a species occur as the intersection between the abiotic and biotic conditions, so the realized niche in the Hutchinsonian niche concept, and dispersal limitation, which define P, place where species occur. So as you have seen, we have different niche concepts that might be also different targets of our models. Indeed, we have several definitions of what might be the target of our model, and Michael Kearney in this very nice paper tried to summarize a bit what we are modeling, if it is the habitat, if it's the niche, or if it is the environment. So I really encourage you to have a look to this paper because I found it very, very inspiring. But in the end, independently of the target of our model, what we are modeling is essentially, again, a relationship between the species and the environment, as we have seen for our mushroom example. And we have different tools for doing this. And today I'm going to present you just two approaches. One are the so-called the correlative approach, and the other one is the mechanistic approach. Again, if we start from the Hutchinsonian niche concept, we have the what was the Grinnell, the Grinnellian niche concept, so the blue circle, which is also called in Hutchinsonian term the fundamental niche. So those abiotic condition allowing, in theory, independently the species to exist. And the goal of often of the mechanistic approach is to model essentially the fundamental niche, because often what we do is we try to link a given life history trait, a biological rate of the species, such as, for example, at the eggs hatching rate, to an environmental variable, such as the temperature. So if you could focus, for example, on this simple example, we can imagine that this biological rate is the egg hatching rate, and we have a zero chances of hatching rate at like 5 degree, and the optimum is around 25-ish degree. And we can use this information to inform a model. Again, if we go back to our mushroom example, we have to think a bit to the life cycle of these species, and we know that mushrooms, the Carpophorus, what we usually eat, they release spores on the soil, and the spores, so the point under certain environmental condition, will germinate, create the mycelium, and after a while the mycelium will reproduce and will produce the Carpophorus, so the mushroom that we eat. And again, if we want to try to map and understand the distribution of a given mushroom species, what we can do, we can take a sample of spores, bring them to the lab, and then investigate their germination rate under different temperature condition, which we can then build a curve and use this information to map, for example, the consecutive number of generation that we have over here. This is just an example. And we can, the nice thing is that we can map these outputs, and we have a really clear causal link between the biology of the species and the environmental conditions. Another approach is the so-called the correlative approach, where, again, taking into account the Hutchinsonian concept, whilst the mechanistic approach focused mostly on the fundamental niche, the correlative approach focus on the realized niche. So the overlap between the biotic interaction, the abiotic conditions. And to do so, what we do, well, again, what we usually collect presence and absence, and most likely presence and background point of pseudo absences, and we link them to environmental conditions. And then we use this information to inform and train an algorithm that will give us as an output the probability of finding these species under different environmental conditions. To inform these models, again, we have observation in the geographic space, and we can use different environmental layers, such as the temperature, the precipitation, but we can also use remote sensing variables. In the end, what we have is this simple workflow where we have this response variable, the present and absence of the species, a bunch of covariates. We combine them into an algorithm, and the output of the algorithm will show us the predicted distribution of the species. Something like the map that we saw at the beginning, showing the habitat suitability for the yellow fever mosquito. Both approach have their pros and cons. And as you can see in this nice summary provided by the Evans, Diamond, and Kelly in 2015, they might also produce different results. And we see that correlative models and mechanistic models, in this case, they predict different ranges of the species. The important thing is to understand why they are producing different estimates and how the models were designed. Because in the end, models are just a way that we try to use to infer and understand the reality around us. And both approaches have pros and cons and some limitation, of course. We try to focus now to limitations. For the correlative approach, we have data quality We have sampling size, for example, so the amount of data we use to inform the model. The selection of variables. Nowadays, we have a lot of potential environmental variables to use to inform our models, and it's important to do ecological informed selection of these variables. So not just to select them randomly, or just to select them and then let the algorithm pick up those that are most important. Another issue is often the lack of a proper external validation. We don't often have the data to validate this model properly. We use often just a subset of the training data set, and this might impact also on the validation of the model itself. The model tuning, so it's important to, in case you use machine learning approaches, to properly tune the hyperparameters of the algorithm. In case you focus on linear models, is important to carry a rigorous model selection. And I think it's important to pay a lot of attention to try to incorporate as much as biology and biological realism as possible into the model definition, to avoid the issues related to extrapolation into different environmental conditions than those used to train the model. On the mechanistic side, we have a similar issue. We have data quality again and lack of biological observation, because as you can imagine, understanding the relationship between a given life history trait and environmental variable is really costly in terms of time and efforts of the experiments you have to carry on. And the experimental setting is often complex, and it takes a lot of resources to carry on this experiment, and then often it lacks proper validation again. So it's difficult to find proper external data for external validation. But in general, this modeling approach have their pros and cons, and it really depends on the question you have behind your model. And I invite you to have a look to these papers, and which they nicely resume the pro and cons of the mechanistic and correlative approach. But in general, to conclude, I really like this representation of the modeling framework proposed by Zurel a couple of years ago, where it really, instead of a straight workflow, she proposed a more circular approach, where we start to a conceptualization of our model, try to understand clearly what are the questions we are trying to answer, and then we start into the data preparation, model fitting. So you prepare the data accordingly to the model you want to fit. You want to assess the model, the quality of the model, if it's realistic, if it's biologically meaningful, if it's statistically accurate, and then you predict the model estimates in time and space. And then if your prediction are not good enough, or you don't think that they are good enough, you can start again from the beginning. So to refine your question, to refine your data, and so on. So to conclude, I think it's important to keep in mind the biology and the ecology of the species of interest when you start preparing your species distribution models, and also think that models are often useful as a food for thoughts, because during the modeling framework you can maybe not find an answer, but find other interesting questions. Thank you for your attention, and I hope you enjoyed.